Hello, good afternoon, friends. Yesterday we have seen the two problems of the no load current. Now it is very important, which is based on the almost derivation. The problem is like that given, and data should be taken from previous problem only. BM flux density and MMF per meter and iron loss watts per kg. The things are given. This problem is asked number of times in the VTU examination for 12 to 14 marks. So you take the careful HV voltage per phase. It is a given problem is a three phase problem. Then HV winding, primary winding per phase. Given voltage is line voltage 33,000 divided by root 3, 19,000 volts. We are getting the per phase. Then this per phase voltage equal to this equation 4.44 F phi m into Tp. From this expression we can find out phi m. Phi m we are getting the 0.191 Webers. So after knowing the flux, then you can go for the flux density in limbs, that is flux density in yokes, that should be given by phi m divided by area of iron, AI. We are getting 1.27 Webers per meter square. So after knowing the flux density, we have to go for the BAT curve and we have to go for the flux density versus loss per kg curve to get the data. For example, now corresponding to this 1.27 Weber city, so from the graph, ampere turns per meter is 560 angstrom per meter. Then loss per kg, it is 2.25 watts per kg. Last previous problem, we are getting the values directly. Then there is no necessity of plotting the graph. Now these values are intermediate. You must have plot the graph. Then you can go for the flux density in yokes. So Bm yoke equal to phi m divided by area of yoke. It is printed as AY. Area of yoke is 0.18, so we are getting 1.6 Webers per meter square. Again, corresponding to this flux density, go to the help of graph. 80Y mmf per meter of yoke, it is 260 angstroms per meter. Loss per kg, it is 1.4 watts per kg. These data are taken from the graph. And then this is the some example and respective graph of BAT plot. You have to plot the graph by taking suitable x and y axis. It is typical I plotted. Same thing, it is almost. You plot the neat graph approximation. You may get the data selection for 1.27 flux density, how 560, 1.27 how loss per kg graph you have to plot if necessary. Then after calculation of this, you can go for the total MMF for 3 limbs. Total MMF for 3 limbs, 3 times of core MMF into length of flux path in core as per the derivation. So 3 times of 560 into 2.3, we are getting 3860 angstrom. Then total MMF for 2 yokes, that is 2 into MMF per meter of yoke, 2 into 80Y into LY, length of flux path in core. That value we are getting 832. Then MMF per joints, the data is not given, you can assume that is 0. Hence, earlier expression total MMF for 3 total MMF should be equal to MMF for limbs, MMF for yokes, MMF for joints. MMF for joints is taken as 0. So MMF for limb and yokes 4692. It is not 80 knot. Again the problem is 3 phase. So total magnetizing MMF per phase. Very carefully, this problem is 3 phase. This above equation gives total MMF. So magnetizing MMF per phase, that is 80 knot. 80 knot equal to total magnetizing MMF divided by number of phases. That should be equal to 1564 angstrom. This is very important. After finding the 80 knot, rest of problem process same thing. So first one, you calculate the magnetizing current per phase, IM. So 80 knot magnetizing MMF divided by root 2 Tp. Then you can go for the TP is given, go for that 2.46 ampere. Then to find out the loss component of no load current, volume for 3 limbs that should be equal to 3 times of AI into Li, that you are getting the meter cube. Then weight of 3 limbs, volume into density, volume meter cube, density is kg per meter cube, meter cube will going to cancel, you are getting the kg. Similarly, volume for 2 yokes, that is 2 times of Ay into Ly. Then again same thing, weight of the 2 yokes, volume into density of yoke respective. This problem process or based on derivation. So loss in limbs, that is total weight in kg of core respective, and loss per watts per kg, again kg will going to cancel, we are getting the loss, total loss in limbs 18.2 into 10 to the power of 3 watts. Similarly, loss in yokes, that also similarly yoke weight and loss per kg of yoke, we are getting the 6.3 into 10 to the power of 3 watts. After knowing these two loss, limbs loss and yokes loss, total iron loss, that is addition of loss in limbs, loss in yokes, we are getting the 24.5 into 10 to the power of 3 watts. After knowing the total iron loss, again we want to convert into per phase. Total iron loss per phase, that should be equal to total iron loss divided by number of phases. You are getting the 8.16 into 10 to the power of 3 watts. So next, loss component per phase. After knowing the iron loss, IL equal to PI divided by VP, whereas PI iron loss per phase, VP primary voltage per phase. So that should be equal to 0.427 ampere. Lastly, after knowing the IM magnetizing current per phase, and after knowing the no loss component of no load current per phase, hence no load current per phase should be given by final expression under square root of Im square plus IL square. It becomes 2.5 ampere